4.0.0 Motor enclosures, frame designations, and operating characteristics. Identify types of motor enclosures, identify NEMA frame designations, identify motor operating characteristics using nameplate data. So, 4.1.0 motor enclosures. It says motors are usually designed with covers over the moving parts. These parts, called enclosures, are classified by NEMA, it's the National Electrical Manufacturers Association, according to the degree of environmental protection provided in the method of cooling. It says if the cover has openings, the motor is classified as an open motor. If the enclosure is complete, the motor is classified as totally enclosed. So here are some open and totally enclosed motors. A general purpose motor, drip proof, splash proof, guarded, semi-guarded, drip proof, guarded. The totally enclosed enclosures are non-ventilated, fan-cooled, guarded, explosion proof, dust proof and ignition proof, pipe ventilated, water cooled, water to air cooled. They're completely encased so that if they are in an explosive environment, they're hermetically sealed and the sparks contained in the motor will not ignite the environment outside of the enclosure. They're totally enclosed, especially the ones that say like explosion proof, dust proof, and ignition proof. Open motors. The most common type of motor is the open motor. It has ventilating openings that permit the passage of cooling air over and around its windings. If these are limited in size and shape, the motor is considered protected because it is protected from any large pieces of material that may somehow enter the motor, thus damaging the internal parts. So if you have a motor in your backyard, maybe a swimming pool, it's an open motor, but it keeps rain out, it keeps water out, it keeps debris out. General purpose, this type has ventilating openings that permit the passage of external cooling air over and around the windings. Drip proof, its ventilating openings are constructed so that successful operation is not affected by drops of liquid or solid particles that strike or enter the enclosure at any angle from 0 degrees down to 15 degrees. Splash proof, ventilating openings are constructed so that the successful operation is not affected by drops of liquid or solid particles that strike the enter the enclosure at any angle not greater than 100 degrees downward from the vertical. Guarded, the openings giving direct access to the live metal or rotating parts are limited in size by the structural parts or by screens, baffles, grills, extended metal, or other means to prevent accidental contact with hazardous parts. Semi-guarded, some of the ventilating openings, usually on the top half, are guarded, and in the case of a guarded motor, but the others are left open. Drip proof, this type of motor has ventilating openings like those in the guarded motor, externally ventilated, pipe ventilated, weather protected, type 1. Ventilation passages are designed to minimize the entrance of rain, snow, and airborne particles to the electrical parts. Type 2, in addition to the enclosure for a Type 1 motor, ventilating passages are at both intake and discharge are arranged so that high velocity air and airborne particles blown into the motor by storms or high winds can be discharged without entering the internal ventilating passages leading directly to the electric parts. Sealed windings. Here's a highlight. It says an AC squirrel cage motor consisting of form-wound coils and insulation systems that uses materials, processes, or both to seal the windings and connections against contaminants. They have totally enclosed motors. These are non-ventilated. They're not equipped for cooling by means of external to the enclosed parts. Fan cooled, they're equipped with for exterior cooling by means of a fan or fans that are integral with the motor but external to the enclosed parts. Fan cooled guarded, all openings giving direct access to the fan are limited in size by design of the structural parts or by screens, grills, expanded metal to prevent accidental contact with the fan. Explosion proof. I think this should be a highlight. Designed to withstand an internal explosion of a specific gas or vapor, it also prevents the ignition of the specified gas or vapor in the surrounding environment, which may be caused by sparks, flashes, or explosions within the motor enclosure. So it's like hermetically sealed. It keeps the sparks from the motor from igniting the atmosphere outside of the motor. Dust proof and ignition proof, designed to keep out dust that could ignite or affect performance or rating. It prevents arcs, sparks, or heat inside the enclosure from igniting dust accumulated outside or suspended in the vicinity of the enclosure. Pipe ventilated, actually has a pipe that goes outside of the room. Openings are arranged in a way that when inlet and outlet ducts or pipes are connected to them, there's no free exchange of the internal or external air. Water cooled, cooled by circulating water with the water or water conductors coming in direct contact with some parts. And water to air cooled, it's cooled by circulating air, which in turn is cooled by the circulating water. NEMA frame designations. Frame sizes were developed by NEMA, again, that's the National Electrical Manufacturers Association, to ensure interchangeability of motors among manufacturers. Frame sizes are listed on motor nameplates to provide information about the physical dimensions. So here's a highlight. It says, the distance from the motor feet to the shaft center line is the D dimension. So here from the motor feet to the center line of the shaft, that's the D dimension. And both hole center to center distance between front and back feet is the 2F dimension. Well, we can't see that when it's sideways. Here you go. Looking at it sideways. From center to center of the anchoring bolts is the 2F dimension. All of these dimensions are given, and it's in the name of the actual motor. It's in the number. Manufacturers create tables to correlate a motor's frame size to its dimensions. An example is shown in Table 2. The system for designating the frames of motors and generators consists of a series of numbers in combination with letters. So the first two or first three digits give you in, what was it, eighths of an inch. So if this is, oh, it's a quarter of an inch, excuse me. So 16 quarters of an inch, it's 4 inches, the D dimension. Remember that D dimension being from the bottom of the feet to the center line of the shaft. So the first two digits is in fourths of an inch, quarters of an inch. So 16 quarters of an inch is 4 inches, and 20 quarters of an inch. See, this should be 5 inches. I don't know why they have it there as 200. 210 is 5, 220 is 550. 250 is 625, 6.25 inches. And then the third and fourth digits in the frame number will actually increase that number. All right, so the first two numbers in the frame size. Let's look at an example. Let's say the first two digits are 16 or 160. It's the 160 series, but if the first two numbers are 1 and 6, then the D dimension from the feet to the center line of that shaft is 4 inches. And then the third digit is going to be the 2F dimension. And if you remember, that was the dimension between the bolt holes, the center of the bolts. So let's say it's 164, then it's going to have 5 inches between those bolt holes. So 4-inch D dimension and 5 inches between the bolts. And this is the chart that they go off of. So we can see that here. They're going to give us an example. It says, here's a highlight. The frame number for the small motors is the D dimension in inches multiplied by 16. The following letters immediately follow the frame number to denote variations. I don't know why they said 16. I think it's times 4, to be honest with you. Well, those are for small motors. And they have these variations G is a gasoline pump motor. So carbonator pump motors, B, motors that are face mounted, are C. I have G highlighted there. But medium frame, here's where we have that D and the 2F dimension. This figure 55 shows a typical end view of a foot-mounted motor. Many different dimensions can be found on the dimension sheet. The NEMA frame designation will provide information related to both the D dimension and the 2F dimension. So the first two digits will be that D dimension. And again, it's the D dimension times 4. So common medium-sized motor frame number is 256. So the first two digits is 25. If you divide that by 4, it's 6 1/4 inches. And it's in the 250 range. So if we look at the third digit, 6, we can see on that frame, here's the 250, and here's 6. 6 on the 250 frame is 10 inches. So the D dimension is 6 1/4 inches, and that 2F dimension between the bolt holes is 10 inches. That's what they're saying. Okay. Let's go back to the example. Where did I go here? I've lost it. Here we go. All right. To determine the 2F dimension, use table 2, and the third digit of the frame number. Third digit is a 6, and the frame is a 250 series. Using the table, the 2F dimension is 10 inches. The T in the frame number is included as part of a frame designation for which standard dimensions have been established. So, medium-sized frames can have multiple letters that denote a variety of different applications and arrangements. A 256 AT has the same dimensions with the A added to denote an industrial DC motor. So, a frame has a D dimension of 3.5 inches and a 2F dimension of 4 inches. So 3.5 and 4, if we went up to this chart, we could find the 3.5 is a 140 series and 4 is 3, so the number should be 143, 143T. So let's see what they've got. Because it's a standard dimension frame, the letter will be the suffix. The frame has a designation of 143T. So the 3.5 times 4 is 14, and then the 140 frame series, a 2F dimension of 4 inches is provided. The third digit is 3, so it's 143T. All right. You don't have to memorize that. Motor ratings and nameplate data. An electric motor nameplate can include the following ratings: the voltage, the amperage, the speed, the horsepower, the NEMA design letters, insulation class, frequency, service factor, NEMA kilovolt amp code letter, bearings, power factor, and the duty rating. So here's a typical motor nameplate. It tells you it's 230 volts. The amps are 13 amps. It shows you actually that they're saying it's dual voltage. I don't know why they would show us dual voltage if it only has one voltage of 230 volts. This should either say 230/460 or 120/230, 115/230. NEMA design letter B. So the frame is K184T. It's 3-phase, 60 hertz. Service factor of 1. We'll talk about service factor later on. And the KVA code is H. Type PF. Power factor is 85.7. NEMA nominal efficiency is 86.5%. It's a 5 horsepower, 1740 RPM. So there are two voltage ratings to be considered: the nominal voltage and the minimum starting voltage. The nominal voltage is assigned as the voltage rating at which the motor is designed to operate. The minimum starting voltage may be defined as the lowest voltage at which the motor will start without drawing excessive current and tripping the protective device. So here's rated voltage and system voltage, induction motor voltages. So they're going to say 230, but it operates at 240. 440. 460, they're going to say it operates at 480. 575, it operates at 600 volts. So many three-phase motors have multiple voltages listed on the nameplate, for example, 230, 460. It means the motor can be connected for either 230 volts or 460 volts. You have to rewire it. You can't just use the same hookup. If you're going to do it in low voltage, you want to operate this at 230 volts, it's going to draw 66 amps. You hook up 1 and 7. This is the 9 leads in the casing. 1 to 7, 2 to 8, 3 to 9. Tie 4, 5, and 6 together. I can tell you right away that this is a Y wired motor between delta and Y. This one's wired Y because we're hooking 4, 5, and 6 together. And if we wanted to put it in high voltage, we'd put 4 to 7, 5 to 8, 6 to 9, and 1, 2, and 3 are our leads out. We'd connect that to the incoming power. The amperage rating on a nameplate indicates the current the motor will draw at nameplate horsepower, frequency, and voltage. So here's a highlight. This is typically referred to as the full load amps, FLA. Let's see if they put that on here. Full load amps. 25 horsepower, 1740 RPM. Service factor of 1.15. Yeah, they didn't put full load amps, they just put amps, 66 or 33. Notice how if you hook it up for 460 volts, it's only going to use half the amperage. We'll discuss that later. The NEC requires that the rated full load current be the basis for determining the proper sizing of cable, overload protection devices, and other overcurrent protection in the motor circuit. Because many motors can be connected to more than one voltage, they have multiple full load amperage ratings. National Electrical Code is going to tell us for standard motors, we're going to use tables 430.2, 47, 48, 49, and 50, 247, 248, 249, and 250, to determine the full load amperage of that motor going by horsepower and voltage. If it's a three-phase, 5 horsepower motor, we'll go to 430.250, and we'll look to see what the amperage rating is. And that's what we'll use to size the cable, the overload, the overcurrent protection, any disconnecting means. The only thing we'll use the nameplate for is the overloads. We will go by the nameplate rating amperage for the overloads. That's in 430.6. You can see that in the code book. Full load amp ratings are guaranteed if the induction motor is operating at full load conditions and at the applied voltage and frequency are the same as stated on the nameplate. So here's a code letter. It says service factor. Well, I'm not sure if they're talking about that. 110% of rated voltage, there's going to be a 7% decrease in the full load current. 90% of the rated voltage, there's an 11% increase in the current. So it's funny. It's kind of counterintuitive because we're thinking of Ohm's law. We think that if we increase the voltage, we're going to increase the current, but that's not true. If we increase the voltage, we're going to increase the speed of the motor, which is going to increase the counter-electromotive force, which is going to reduce the overall current. If it's running at only 90% of voltage, it's going to be running slower. It's going to be producing less counter-electromotive force. The current's actually going to increase. So, starting current, the total instantaneous starting current comprises the locked rotor current plus the transient inrush that flows until the motor magnetic field stabilizes. It's only for a split second. A couple of half a second, 1 second, 2 seconds, that thing is rotating and it's creating CEMF, and it should be up to speed within 3 seconds. The rated full load speed of is the value indicated in RPMs on the nameplate. It's the speed at which the shaft will turn at the nameplate horsepower when supplied with power at the nameplate voltage and frequency. If the driven load is less than the nameplate horsepower, the shaft will turn faster than the full load speed. If the motor is operating in an unloaded condition, the shaft will turn very close to synchronous speed. For example, with a full load speed of 1,740 RPM, it can be inferred that the motor's synchronous speed is 1,800 RPM. The motor will operate from close to 1,800 RPM down to 1,740 RPM with rated no load to full load condition. Horsepower. An induction motor is essentially a torque generator. It delivers a needed torque to a driven motor at a certain speed. Although the torque and horsepower are closely related, they're not the same thing. Torque is the twisting force of a motor, and horsepower specifies the rate or speed of this force. So they give you a formula. Load torque in foot-pounds times the rotations per minute divided by 5,250. It's a mathematical constant, and that equals the horsepower. Here's a highlight. So standard motors are designed to operate at nameplate values from sea level up to an altitude of about 3,300 feet. So here's another highlight. It says several methods are available to estimate true motor horsepower output. NEMA design letters. NEMA design letters define the starting torque characteristics of an induction motor. It's one of the most important pieces of information on the nameplate. Unfortunately, when a motor is replaced, the NEMA design letters are usually ignored, often leading to misapplication of the new motor. It says for mixers or loaded conveyor belts, however, starting torque requirements change very little with speed. To account for these differences, NEMA formulated design letters A, B, C, D, and F. The difference among the motors with these letters is mainly the design of the rotor, although there are also a few external differences. Design A and B motors are intended to drive conventional loads such as fans, blowers, centrifugal pumps. About 80% of industrial motors are NEMA design letter B. So there's the NEMA design. Generally, the starting current is about 5 to 7 times the rated full load current. From table 5, you can see that the starting current of a large motor is significant. Cross-line starting of large motors could result in objectionable line voltage dips. These voltage dips could result in other control equipment dropping out because of low voltage and could even cause lights to dim momentarily. So sometimes it's advisable to use a soft start or a variable speed starter so that you're not trying to start it at full load voltage. There are different types of soft starts. Insulation class. The electrical insulation system in a motor is determines its ultimate lifespan more than any other component. Man, I'm going to highlight that. That sounds important. It sounds like something they might ask you. The insulation system in a motor determines its ultimate lifespan more than any other component. By some estimates, over 60% of all motors brought to repair shops are there because of premature failure of the insulation system. The insulation class is a NEMA designation that identifies the class of material used to insulate the windings. 4 letters used to designate the 4 classifications are A, B, F, and H. The insulation class defines the temperature that the insulation can be subjected to without suffering damage. So, Class A is now obsolete. Class A was once the most common classification for motor insulation, especially for small motors. Class A comprises materials or combinations of materials such as cotton or paper when suitably impregnated or coated with to resist heat, or other materials capable of operating at the temperature rise assigned for Class A. Class B is the predominant class of insulation used in motor manufacturing and rewinding today. This class is the basic standard of the industry that includes mica, glass, fiber, polyester, aramid laminates, as well as materials with suitable bonding substances or other materials capable of operation at the temperature rise assigned for Class B. Class F incorporates materials that are like those in Class B but can operate at temperature rises assigned for Class F insulation. And Class H insulation systems comprise, along alone or in combination, silicon elastomer, mica, glass fiber, polyester, aramid laminates, as well as materials with suitable bonding substances for other materials capable of operation at the temperature rise assigned for class H insulation. Did I walk past it? Where did it tell me those? It didn't tell me the temperature. All right. Service factor. The service factor is a multiplier for the nameplate horsepower rating that determines the amount of overload the motor can withstand. So the most common service factor listed on a motor nameplate is 1.15. And I think you could take it to 125%. Where did they tell us that? They did. All right. The letter corresponding to the, this is NEMA KVA code letter. It's the inrush current. The high current draw of the motor during the first moments of startup is called the inrush or locked rotor current. This is the steady state current of a motor with the rotor locked in position and rated voltage applied. It can be derived from the KVA code letter on the motor nameplate. So you can take the KVA of the motor divided by the horsepower. And 0 to 3.14 is on code letter A, 3.15 to 3.54 is letter B, 3.55 to 3.99 is C, and 4.0 to 4.49 is D. The complete table shows the KVA per horsepower value using letters from A to V, excluding I, O, and Q. Figure 60 shows this value on the example nameplate. All right. Bearings. Polyphase induction motors require either anti-friction or sleeve bearings. Anti-friction bearings are standard medium horsepower motors through 125 horsepower and 1800 RPM. They're optional in 150 to 600 horsepower motors operating at 1800 RPM. Sleeve bearings are standard in 500 horsepower motors and larger, operating at 3600 RPM. Sleeve bearings are also used in the smallest motors. Of course, there are always exceptions to these broad ranges of bearing application. Because radial loads are higher at the drive end of the motor, the drive end bearing must have a higher load rating than the bearing at the opposite end. An example of bearing numbers on a motor nameplate is shown in figure 59. Power factor. It's the ratio of active power of an alternating or pulsating current to the apparent power indicated by an ammeter and voltmeter. It's also referred to as the phase factor. Power factor is a measure of the system or equivalent efficiency. And here you go. Here's your duty rating. All polyphase induction motors have either a duty or a time rating, which is the elapsed time the motor can operate at nameplate horsepower without shortening its life. So standard time ratings are 5 minutes, 15 minutes, 30 minutes, and 60 minutes, and continuous. A motor with a duty rating other than continuous is usually a smaller motor that's given a higher horsepower rating for a shorter duration, thus reducing the size and cost. Many motors are capable of continuous service at 104 degrees Fahrenheit, 40 degrees Celsius. The most common motor duty rating is continuous duty, defining the output in kilowatts for DC generators, kilovolt amps at a specified power factor for the AC generators, and horsepower for motors. That can be carried indefinitely without exceeding established limitations. For intermittent duty, periodic duty, or varying duty, motor may be given a short time rating defining the load that can be carried for a specific time. Standard periods of short time ratings are 5 minutes, 15 minutes, 30 minutes, and 60 minutes. Speeds, voltages, and frequencies are also specified in ratings, and provision is made for possible variations in voltage and frequency. So if you have a garage door opener, it's going to be intermittent duty. It's going to have a 5 minute. It doesn't take 5 minutes to put your door up or down. Every time that motor comes to rest, the the bearings and the coils of the motor will cool off. It generates heat while it's operating, but as soon as you stop that motor, it starts to cool off very quickly. So if you open your garage door and you change your mind and you close your garage door and then you change your mind and you open your garage door, you're not going to burn it up. If you did that for a half hour, maybe you'd burn it up. But 3, 4, 5 times, you're not going to burn it up because it's intermittent duty and it can go for as long as 5 minutes in operation. And like I say, it's only running for about 15 seconds. If you have a pool pump, that's going to be continuous duty because they understand that sometimes people will turn on their pool, they want it to run for 3 or 4 hours. So they're going to be there. They will rate that at continuous. They're not going to give you a 60-minute time limit on your pool pump. All right. So motors must operate successfully at voltages 10% above and below the rated voltage, and for AC motors at frequencies 5% above and below rated frequency. The combined variation of voltage and frequency may not exceed 10%. Other performance conditions are established so the reasonable short time overloads can be carried. The user of a motor can expect to be able to apply an overload of 25% for a short period of time at 90% of normal voltage with an ample margin of safety. Okay. Section 4 review. NEMA designation for a type of enclosed motor. Using NEMA frame designations, the distance from the motor feet to the shaft center line. All right. And what characteristic of a motor determines its ultimate lifespan more than any other?